Okay. Shall I start? So, in the second part, I would like to cover mostly in the tomography. I won't take much time. Of course, this is not my expertise that I am trying to develop. So, I am just sharing you what from my knowledge. Okay. Yeah, just to share you, most of the slides that I have shown in the previous, that is from my postdoc. However, in the IISER training that we have already developed the microscopic system. However, I didn't show my results because it is not yet published. This is ready. So, I think it's very clear about the design and development and the reconstructions for the microscopy system. So, now I would like to discuss about the tomography. So it is all about the generations of the photoacoustic signal due to the photoacoustic effect. So this is how that we have seen in the microscopy, and this is about the picking up of the initial pressure rise. However, in the tomography, it is not the picking up of the initial pressure rise. It is a matter of the detections by the transducers by keeping on the boundary of the sample. That is what the secondary pressure that I would like to say, that is the primary that is detecting. Another difference is that in this one we are using the focusing transducer. In this one people are not using the focusing transducer, unfocused and narrow, so that we can achieve the better spatial resolutions. So for the reconstructions of the data, then here is the two methods, design and development, that I will come after this one. So typically it is of the two types that I would like to say. One is the delay and churn or a beam forming. Another one is the iterative methods that involve the solutions of the differential equations. One over here, it is not involving any kind of the solutions of the differential equations. It is very effective. It is a real time for the real time application, for the clinical applications. This is accurate at the cost of time and expenditures. And so I would like to discuss about this delay and churn techniques. What's that? This the whole of the theory of delay and churn is given by this equation. So the signal, as it is collected by a detectors or an array of detectors or detector that is kept around, that is used to construct the distribution of the signal in the domain. In the sense that, just 1 minute ago, I let it here. So in this kind of the detection technique, conventionally what happens is that people use only one single transducer. Then by using the stepper motor, and then it is moving around to detect the signal from the boundary in a 3D or 2D according to that. The quality of the image, it is dependent on the number of the detection positions, of course. Then instead of this one, it takes time. It cannot give the real time. So instead of this time, at the course of the instrumentations, if we are keeping an array of the detectors, we can detect at one time all of the signal around the samples. That is also different. So this is not real time. However, people try to do it real time by increase the expenditure of the systems. So in this way, by saying that what is happening is that we have a sample, we keep them all around the detectors. We detect it. What detect it? Time window photoacoustic signal, where the photoacoustic signal is emitting the surface of the sample. It is collected. From this signal, then we discretize this sample and then mapping the signal with a weighting factor, this one. So at a given point, it is considered as a contribution from all the signal that is detected from here. So this is what I think is very clear. From this one, this is what it is giving. So by using this technique, one can achieve the reconstruction of from the tomography point of view. It is very, very, very effective. Another one, the iterative method. Generally, to the literatures that I found is the FEM-based, Green's functions, and the bond approximations methods that I found used in the K-web. This is an open source, all the people knows that we can use it from the Wahlberg's groups. And another one is the Monte Carlo that I saw it. So the whole purpose of this one, of this iterative method, is for the solutions of the second order differential equations either in the time domain or in the frequency domain with the initial conditions of initial pressure rise, and then there is no changes in the initial pressure rise with respect to time. With this condition, then one can arrive to this one. With another, it is X-ray condition. The key thing is transient. Okay. From this, by solving these equations, one can reconstruct the distribution of the pressures in a mediums, 3D or 2D. That is the one. So, for the imaging point of view, how to do it? That is the point. So, for that one, I would like to come up with the forward problems and the inverse problems. How we are going to use that kind of the solution of the differential equation for our imaging applications. That is what. Before coming to this one, let me highlight about the problems. So, by the forward problems, what it says is that we know the distributions of the physical parameters in the sample of our interest. So, in our photoacoustic, suppose the distributions of the adsorption coefficients or velocity of the sound or whatever the parameters, elastic property, then we can say whatever the parameters, temperatures, all these things. But by increasing the number of the parameter, accuracy is small, but it is time very expensive. So, to increase the time resolution, then people used to neglect the parameters of our minimal contributions. So, generally people used to do with the distribution of the adsorption coefficients. Until and unless it is quite demanded for the velocity. So, people has already published the papers in the literatures that with the incorporations of the distributions of the velocity of charm, so image is improved. But it is a very, very rigorous process. It takes time. So, with the given distributions of the physical parameters in the samples, for a given input light source, what would be the photoacoustic signal strength with respect to time? This is what we call as the forward problems. Given the distributions, then what would be the measure in the boundary? That is what we call as the forward problems. In the meantime, what is the inverse problems? Given input source, given the measured detected signal, then what is the distributions of the physical parameter of our interest? This is what our imaging people wants. So, how to get it? From the experimental measurement that we can get the measured signal by keeping an array of detectors or an detector unit consisting of an elements of the detectors. From this one, then of course the inputs intensity of the light that we can get it from the experimental fact. Then how to get it? Whether the tissue is diseased or not, or at what stages, all these things that we have to characterize from the distributions of this one. This is our problem. How people used to do it is that by solving the differential equations and implementing the iterative process, one can get it. How in this way? How in this way? So So with the initial guess of the distributions of the mu-A and the quantum physical parameters, then with the initial shows, then we do the numerical solutions of the differential equations. Then from that numerical method, we can achieve the signal strength at the boundary corresponding to the locations of the sensor, in our case transducers. So with the given parameters, with the given source, what is this one? Initial guess. By theoretically we estimate this one, theoretically. Then with these distributions, whether this measurement is matching with our experimental measurement. So is it okay? Shall I move on or shall I? So what is happening is that basically we don't know for an unknown sample what is the distributions of the absorption coefficients or velocity of the sound over the samples. So for this one, when we light is illuminated, experimentally we can keep the detector around. Experimentally we can measure it, but we don't know inside this one. Our question is that how to get this one. So for this one, experimental measurement one set is there. Another theoretically that we will feel that incident beam is there. We will assume the initial guess of the distributions of these mu-A and velocity, and then we solve the differential equation. From that one, theoretically we will estimate this kind of things. Now, then what? We predict that this one. This prediction, whether this is matching with our experimental measurement. If this is not, this is the error of the prediction and our experimental measurement. If this error is less than the error limit, then we consider that this is the distribution of the parameters. If no, then what? We update the distributions of these distributions. Then we measure it. Then we get the error. Continuously processing. So when it is within this one, then we feel that this is one. Then what? How to validate this kind of these systems? So before moving to the unknown sample, what we used to do is the tissue mimicking phantoms with the under the control system where we know the distribution of the absorption. Suppose a whole system with the norm of the absorption coefficient and speed of the sound, and then let's introduce this kind of the target of the non-absorption and all those things. We try it under the control system, then we compare it. If that is true, then we can go to the unknown sample. This is how it is going. This is about the implementations of the reconstruction technique for the photoacoustic tomography. I think in the previous class, someone would have done for a very rigorous for these things. So about the design and developments, as I have told you, so at the beginning, people used to keep it with the one sensor and then it is moving around. So it is time consuming. It cannot get the this one real-time imaging system. The another thing is that if we are making this one, suppose for this collection of these, it takes 5 minutes. Then the incident happening over here, if it is a time dynamics, then we cannot get it. So in such that for this kind of the imaging system, it is limited to the kind of the physical system that is not time barrier within that equation time. Within that equation time, that system should not be changing with respect to time. That is the limitations. So after that, people used to do it with an array of detectors. Even in the 3D, people give it and get it the results. However, still over here, the resolution is very poor. To my knowledge, up to this, what I can say, stage of the development of the photoacoustic tomography, it is limited to the 500 micrometers. meditation that of course it is of the order of the centimeters. Now people start thinking of then how to improve the resolutions. That is what people start thinking of. So this is the kind of the imaging system. That is what we are developing now. So how it is done is that it is a curved transducers of the element of the 512. So the axis of the element, this is the curve. The axis of this element, in the sense that the imaginary line passing through the center of this element, normal to the surface, it is intersecting at the center of the imaginary spherical surface over this part, such that over the center regions, it is highly resolving taken the sample, so that we can use the previous delay and sum or beam forming algorithm other than the solution of the differential equations. So this kind of the technique, it is reported very successful with the element model imaging. So now, other than this one, people already started thinking of, instead of this one, what about whether we can adopt this kind of the microscope, this kind of this imaging system with our conventional ultrasound imaging system, because detection is sharp, only the illumination matters. Then, with this the existing ultrasound probe that is there in the clinical ultrasound imaging, then adopted with the light illuminations. So from this one, light and ultrasound is detected by this kind of things. So for this kind of things, we don't need the kind of the solution to the differential equation, so that it can give the real-time image. This one real-time images. It is shown proof very successful for the reconstruction of the images, and very recently, as I observed in the literature, I am not sure whether I marked the reference. So instead of the laser, people start using with the LED for the light illuminations. The challenge is that the laser is quite volumetric, so energy over a certain area is very high. That is not easy to be achieved by the LED, where they use a good number of the LED. So for illumination, for that one, they got it. So this is the conventional ultrasound transducers. I would like to say these are the state of the art for the photoacoustic tomography. So I am just giving the results. This is the whole body imaging of the rat that I just for the showing capability, I just got it from the Daniel Razansky's group. So it is shown that they can do by using this kind of the cup transducers. In this way, what they are doing is that in the conventional way, what they are doing is that people used to keep this sample, people used to keep the 3D array of the transducer all around. This is the conventional way. Or otherwise, people do the slice, and then do it. So what they say is that instead of this one, this kind of the transducer is moving in the spiral way and then giving the results. So this is that one. Very interesting is that this kind of the imaging system is reported by the Razansky. I think he is from the Technical University of Munich. Now he is moving to the Sweden, I think. So he can achieve with this tomography technique to the 60 micrometers. So tomography is now reaching to the microscopy region. So this is about, and this is about the. So this one, please don't take a photograph because this is not unpublished. This is unpublished, and as well as this is from the visual sonic that I didn't take the permission properly. So this is from the visual sonic images. This is the image from my hand. This is a real time. This is the dual imaging modalities, ultrasound and the photoacoustic. These, if it is the photoacoustic, we cannot get this one. We get only that. I don't include the image over here. With the photoacoustic, we don't get the structure of the tissue. We get only the absorption contrast. But when we are giving to the doctors, what about if we are giving together with the structural information of the tissues? That is what it's doing. So, in this visual sonic imaging system, they can provide the structural information as well as this one. How they are doing is that they are doing in the time sharing mode. So they send the pulse laser and do the photoacoustic. Next time they do the ultrasound imaging. So they combine together. This is the 3D images of the blood vessels. Yeah, this is the imaging system for the visual solids. Yeah, just to share you, I think to my knowledge here is no photoacoustic imaging system, even from the as a clinical use or laboratory use. I heard that this one visual sonic has already installed one system in the night world party. That's what. So I am showing you. So I have shown you just now with the reconstruction results of the reconstruction technique with the delay and sound. So this one I don't have any of the real sample results. However, I am showing with the simulation results that we have carried out. So we assume that this is a sample of interest, target of interest. Then we keep it inside the background sample, considered as a water, and then we keep an area of the detector, and then we use the K-wave, that is the open source, and then we do it reconstruction. It was quite successfully. What we propose is that in the standard way, the conventional way of for the reconstruction of the photoacoustic tomography, people neglect the acoustic signal coming from the background. In the sense that for the ultrasound imaging, we need to immerse the sample inside a background. Suppose whenever we are doing the ultrasound imaging, we need to put the gel or keeping inside the water. That is because of the proper signal coupling of the ultrasound signal to reduce the loss of the signal due to the reflection at the interface. So in that way, people neglect for the simplicity, for the simplification, the signal coming from the water or from the gel. What we studied was that whether it gives a signal, though it is minimal. If that is the case, whether we can discriminate that signal, and then in result, what is the improvement in the imaging? That is our concern. This is the standard technique. Then one is that the signal that we got it from the background, and with the signal that we got it from that one, then we do the difference, subtract it out, discriminating from by the considering that the noise from the background is additive in nature. Other one that we consider that is multiplicative in nature. So we found that considering the multiplications by dividing the signal from here with the background, it gives the better signal. This is the characterization. So that we call as the bone ratio type data normalization that gives the better signal. So this is about some other numerical samples that we did it. So the image was found to be quite improved. So another one, this is our results that we are trying to build up the tomography system. In the meantime, we are carrying out the simulations by using the K-wave. For this kind of things, we are building up through the simulations the area of this one, and then we are using this kind of the targets that we use it, and then this is the reconstruction. So it is reasonably okay that we are improving now. We are trying to improve now. And then we are trying to get it with this one, simulated and one, two object rest together, and then we do the reconstruction. It is quite successful with this kind of the transition system, and then with the K-wave. However, the K-wave is not the real time. Our objective is that with this one we should adopt with the delay and some algorithm so that we can achieve the real time imaging systems. So this is only the simulation system. So from the iterative process that involves the solutions of the differential equations. So this is from our postdoc lab that I was not involved with, however I give the citations. So this is what. And then the one interesting over here is that people already developed the photoacoustic system that can be adapted to the mouse. That can be where the mouse is not required to be anesthetized. So experiment can be conducted in the allied conditions. They can move very freely. That one, they move it all around. So definitely I have seen during my stay it was done. So they picked it over here, then red are all around. So this is about the study of the epilepsy. So this is the state of the art. So the kind of this one transducer is quite different. This is the very minor transducer. I think they are using not more than 158 element. I think around 64 element they are using. So they are getting this kind. This is the state of the art. Yeah, one more that I would like to discuss. This is the last part. From the microscopy that I have shown that velocity of the sound and the velocity of the flow that we can measure, elastic property that we can measure. In a similar way, what are the other physical parameters that we can extract from the measured photoacoustic signal? So from the photoacoustic signal that we can get the distribution of the absorption coefficient that we know, that I have already discussed. Now, here is one technique that we call as the spectral unmixing technique, where we explore the dependence of the absorptions with respect to the wavelength. So, if that is the case, this absorption is contributed by the number of the chromophore that is there in the sample. That is given by the alpha and this is the concentration. This is the extinction coefficients. That is independent of the concentrations. However, the concentration is independent of the wavelength. So this is the linear equations. Then what? If we measure these absorption coefficients for a various wavelength, then we can have the number of equations. Where this is done from our experimental measures, from our established literature. This is the concentration that we want to measure for a unknown sample. What is the concentration of the hemoglobin? What is the concentrations of the oxygenated hemoglobin and all these things that. So if we expand this one from this system of the linear equations from the measurement of this absorption coefficient at a different wavelength, this, if it is equal to the number of the component under consideration by solving these differential equations, then one can get the distributions of the concentrations of the chromophore in the system. From that one, we can recover the physiological information of the system. So this is also a typical results where it shows the distributions of the HB, HbO2, and of water and the velocity of sound. I think in this order. So this is the HB, HbO2, and the water and the velocity of sound. This is in the small element models over these regions. So this is what I can say. This is about the tomography. With this one, I like